Hello students, this is our physics chapter number 4, moving charges and magnetism. We are going to talk about the solenoid and toroid. You have learned about a bar magnet in your previous standards. The magnetic field lines of a solenoid is same as that of bar magnet. We had two poles in bar magnet. First one is north pole and second one is south pole. The magnetic field lines of a solenoid is same as the bar magnet. We are going to talk about a solenoid first. Solenoid we have considered here a long solenoid. Long solenoid means the length of solenoid is large compared to the radius. The solenoid is large, that means the length of solenoid is a large with respect to its radius. So that is called a large solenoid. Second one is wire wound in Harris. How can we make a solenoid? So simply we can make a solenoid with a wire wound in a helical shape, in a helix form. If we take a pen, simple pen, and we wound the wire on it in a helical shape, and at last we remove the pen from it, then the shape that we have is a solenoid. It has two ends. Solenoid, we can see the figure of solenoid over here. In solenoid, closely spaced wires are wound, which are separated from each other by the insulating material. Net magnetic field is vector sum of the fields due to all the turns. As we have discussed earlier, every current carrying conductor produces a magnetic field around it. So in solenoid, we have so many turns which are wound in a helical shape or helix form. So each and every turn will form a magnetic field, which will be in a round shape around it. So total magnetic field produced by the solenoid is sum of separated wire or sum of separate turn. The magnetic field, total magnetic field of solenoid is the vector sum of the fields due to all turns. So this is the way in which we can find the total magnetic field of solenoid by summing up the whole magnetic fields of a turns. So this is our solenoid. These are our magnetic field lines. This is our turns. We can see here turns. So we can see here that the magnetic field in center of the solenoid is parallel. The magnetic field lines are parallel in the center of the solenoid. So we can say that the magnetic field will be uniform at the center of the solenoid. Once again, in the center of the solenoid, the magnetic field lines are uniform. So we can say that the magnetic field will be uniform in the center of the solenoid. We can see the cross section of the solenoid over here. So these are the dots suggest that the wire is coming out from the plane, and cross suggests that the wire is going inside the plane. So we have taken here ampere and loop, which is denoted by ABCD. This dotted line, we have drawn the ampere and loop with dotted line The P is the point which is inside the solenoid and Q is the point which is outside the solenoid. These are our field lines we have drawn here. And now we can say that ABCD is ampere loop. DC, about DC, where is DC? So DC. So the side DC of this rectangle is outside the solenoid. So the magnetic field along DC is 0. Now another two sides AD and BC. Another two sides AB, AD and BC. The magnetic field component along this direction is 0. So we can say that BC and AD, the component of magnetic field is 0. Now the remaining side is AB. So let the distance between A and B, or the length of the side of rectangle ABCD of side AB is AB equal to H. We have written here the distance between A and B is H. So now field along AB is B. Let me assume that the field along this side AB is capital B, length of loop L equal to H. So now distance between A and B, which we call the length of the loop, is H. N is the number of turns per unit length. We have denoted here small n for number of turns per unit length. Now total turns equals to number of turns per unit length into total length. So total length equal to H and number of turns per unit length is N. So we can get the total turns. Total number of turns equal to N into H. Total current equal to I into NH. Because NH is equal to the total number of turns. So if we want to find the total current, so we have to multiply current with total turns. So total current I is equal to I into NH. From Ampere's circuital law, now we apply here Ampere's circuital law. Close integration B dot dl equal to mu 0 I. So B dot dl. So integration of dl is total length. Total length we have taken is capital L equal to mu 0 into IT. IT is the current enclosed by the loop. So BH, we have taken the length of the loop L equal to H. So we have replaced L with H. Now mu 0 IT is the total current enclosed by the loop. So IT equal to I and H. So we have written here I and H. H and H will be cancelled over here. Now we get the B equal to mu 0 into Ni, which is the formula for the magnetic field of a solenoid. This is the formula is magnetic field of a solenoid, which is equal to B equal to mu 0 and I. B equal to mu 0 and I. Here mu 0 is the permeability, N equal to number of turns per unit length, and I is our current. So we can get the formula of a magnetic field produced by a solenoid, which is equal B equal to mu 0 and I. Now if we go forward, we will talk about the toroid. Toroid is nothing but it is one type of solenoid. If two terminal of a solenoid we join together, so that will be a toroid. Toroid is nothing but it is one type of solenoid. So if solenoid bent into circular shape, if we have the solenoid and if we bend it into the circular shape, so that will become a toroid. Let magnetic field, we can see in this figure that we have toroid. This have here sectional view of a toroid, we have taken here 3 ampere loop which is denoted by dotted lines. So this is our internal first loop, this is our second loop, and this is our third loop. 3 ampere loops are drawn by dotted line over here which are ampere loops. So now if let the magnetic field due to the loop 1 is innermost side of the circle, this is denoted by 1. So current enclosed by that loop is 0. So let the magnetic field due to the loop 1 is B1 and total length of that loop L equals to 2 pi R1. So from the ampere circuital loop, if we apply here circuital law, now if B1 equal to B1 into 2 pi R1 equal to mu 0 into 0, because the value of I is 0 over here. So B1 equal to 0. Now if we talk about another loop number 3, so let the magnetic field along the loop 3 is equal to B3 and length of the loop is 2 pi R3. R3 is the radius of that loop. So current enclosed by this loop will cancel each other. How? So here loop number 3 we can see the magnetic field lines coming out from the plane and going inside the plane will cancel the effect of each other. So the net current over here that will be 0. So the magnetic field due to loop 3 also will be 0. Now the remaining loop is loop number 2. Now magnetic field inside the solenoid is B. Suppose the magnetic field inside the solenoid is B. Length of the loop is 2 pi R. I is the current enclosed by the loop, and if we apply here ampere circuital law, so close integration B dot dl equal to mu 0 I. So B dot dl. So close integration dl, that means the total length of the loop which is equal to its circumference. So 2 pi R is total length equal to mu 0 and total current is N into I. N is the total number of turns of that loop. Now if the 2 pi R will change the side, so that will go into the denominator. So we can get the formula of the magnetic field produced by toroid, mu 0 N I upon 2 pi R. This is the formula of magnetic field produced by toroid. So if we change some things in this formula, so we can take the N upon 2 pi R. N is total number of turns and upon 2 pi R. 2 pi R is the total length of that loop. So if we take the ratio of N upon 2 pi R, that will be small n. Small n suggests that N upon 2 pi R, small n is the total number of turns per unit length. What is N? N is number of turns per unit length. N is number of turns per unit length. So we can write this formula in this way also. B equal to mu 0 N I. This is the N and the value of small n is equal to capital N upon 2 pi R. So in this way we can get the information about the solenoid and the toroid. We will discuss more about this topic in depth in our next session. Thank you.